Dear viewers, good morning. I welcome you all to this SWAM platform. The course name for this presentation is Power Generation Technologies. The topic will be covered is Rankine Cycle. I am Dr. Suraj Kumar Mukti, Associate Professor in the Department of Mechanical Engineering, National Institute of Technology, Raipur. This will be the content of today's presentation. Initially, we will know about the introduction of the thermal power station. Then we will go for the working principle of the thermal power station. Then what types of thermal power cycles are available for thermal power station, we will classify that cycles. Then we will enter into the thermodynamic cycles. An overview will be given here in this topic. Then we will introduce about the Carnot cycle. Some introduction and application of Carnot cycle will be presented over here in this section. Then we will enter into the Rankine cycle. What is the Rankine cycle? What is its introduction? We will discuss about the Rankine cycle in this section. Then what is the working principle? In which working principle the Rankine cycle works? We will discuss about this principle in this section. Then we will enter into the construction of Rankine cycle. Then we will discuss about the working of Rankine cycle. Then what type of energy is there. So, energy analysis part of Rankine cycle will be covered here in this section. Then we will discuss about the efficiency, Rankine cycle efficiency, what is called as efficiency of Rankine cycle, and then we will enter into the improvement of Rankine cycle efficiency, how the efficiency of Rankine cycle can be improved, we will see here in this section. And then we will see the comparison between Carnot cycle and Rankine cycle. Now, enter into the thermal power station. What is called as thermal power station or thermal power plant? A thermal power station is a type of power station in which heat energy is converted into electrical energy. In a steam generating cycle, heat is used to boil water in a large pressure vessel to produce high pressure steam, in which drives a steam turbine connected to an electrical generator. The low pressure exhaust form the turbine entrance a steam condenser, where it is cooled to produce hot condensate, which is recycled to the heating processes to generate more high pressure steam. This is known as Rankine cycle. A thermal power station works on the basis of principle that heat liberated by burning fuel is converted into mechanical work. Mechanical work is converted into electrical energy with the help of generators. It is a thermodynamic cycle that converts heat into mechanical energy. Thermodynamic cycle is a series of operations involving heat source, a heat receiver, machine or utilizer between the source and the receiver and the working substances. Now, we can classify the power plant cycles. Thermal power plant cycles work on vapor cycle or gas power cycle. So, basically we can classify power plant cycle in two broad categories. Number one is classification on the basis of vapor power cycle, and second is classification on the basis of gas power cycle. So, here we can mention that on the basis of vapor power cycle, we can subclassify this cycle in four categories. Number one, Rankine cycle, number two, reheat cycle, number three, regenerative cycle, and number four, binary vapor cycle. Whereas the gas power cycle can also be subcategorized in four categories. Number one, Otto cycle, number two, diesel cycle, number three, dual combustion cycle, and number four, gas turbine cycle. Here we can see an overview of various types of cycles and their isentropic steps. I would like to show a few cycles related to this isentropic steps are: number one, ideal Rankine cycle, where in 1 to 2 isentropic compression in a pump is there, and when I take ideal Rankine cycle, the process isentropic step is 3 to 4. The expansion of turbine is shown in 3 to 4. Ideal Carnot cycle in 2 to 3 shows the isentropic expansion, whereas 4 to 1 shows the isentropic compression. In Otto cycle, we can see the process from 1 to 2 is isentropic compression, whereas in the same cycle the process 3 to 4 shows isentropic expansion. Taking the case of ideal diesel cycle, where the process 1 to 2 shows isentropic compression, and in the same cycle the process 3 to 4 shows the isentropic expansion. Taking the example of ideal Brayton cycle, 1 to 2 process shows the isentropic compression in a compressor, whereas the process from 3 to 4 shows the isentropic expansion in a turbine. Ideal vapor compression, 1 to 2 shows the isentropic compression in a compressor, whereas 2 to 3 shows the isentropic expansion in case of ideal linear cycle. Now, taking the case of Carnot cycle, Carnot cycle is an ideal thermodynamic cycle proposed by French physicist Sadi Carnot in 1824 and expanded upon by others in 1830 to 1840s. By Carnot's theorem, it provides an upper limit on the efficiency of any classical thermodynamic engine during the conversion of heat into work. Here in this slide, we can see a complete description of Carnot cycle, where here there is a sink with high temperature and another sink is kept in low temperature. So, here in this case we can see the heat is flowing from higher temperature to lower temperature. In between we are able to get work out of it. In the same slide we are able to see the TS diagram. T shows the temperature in vertical direction and S shows the entropy in horizontal direction. So, here a rectangular kind of shape is presented here, which shows the work done in Carnot cycle. Another cycle, this is called as TS and PV diagram. So, Carnot cycle consists of two constant pressure operations, which is 4 to 1 and 2 to 3. Here the case is shown in the cycle, and two frictionless adiabatic processes are there. Adiabatic process is nothing but it is a isentropic process. So, isentropic process is shown as 1 to 2 and 3 to 4 in this slide. So, this slide shows the TS diagram and PV diagram of a Carnot cycle. So, what is called as Rankine cycle? Rankine cycle, William John Rankine, a Scottish engineer, has invented the Rankine cycle in 1859. The Rankine cycle was named after him, honoring his contribution to this subject. The Rankine cycle is an ideal thermodynamic cycle involving a constant pressure heat engine that converts heat into mechanical work. The Rankine cycle is an idealized thermodynamic cycle describing the process by which certain heat engines such as steam turbine or reciprocating steam engines allows mechanical work to be extracted from a fluid as it moves between a heat source and a heat sink. What is the working principle of Rankine cycle? Here in this case we can see the Rankine cycle is the fundamental operating cycle of all power plants, where an operating fluid is continuously evaporated and condensed. The selection of operating fluid depends mainly on the available temperature range. It works on the principle of heat engine, which convert the chemical energy of fluid into the thermal energy for the generation of steam. In this slide we can see a working model of a Rankine cycle, where we are able to see the various components of Rankine cycle. Like various components are shown here, like condenser, control rods. This is basically a boiler, and then we go to turbine and generator. Ultimately, using this Rankine cycle, we will be able to get a power in the form of electricity, which may be used in the domestic purpose as well as industrial purpose. So, this picture shows a complete outline of a Rankine cycle. Rankine cycle is the theoretical cycle on which the steam turbine works. It is the thermodynamic cycle that converts heat into mechanical energy. So, ultimately after completion of this cycle, we will be able to get a mechanical energy. In this picture, we are able to see the various components involved in Rankine cycle, like number 1 is turbine and 2 is condenser, and then expansion pump, and then hot well is there, and then feed pump is there, and boiler is there. Various numbers are shown here so that we can mention these numbers in our diagrams also. Like here also we have seen the same thing, and these numbers may be depicted on the PV and TS diagram. The main components of this Rankine cycle is steam boiler, steam turbine, steam condenser and feed pump, and the processes are shown here. Like 1 to 2 shows the reversible adiabatic expansion in the turbine, and 2 to 3 shows the constant pressure transfer of heat in the condenser, and 3 to 4 shows the reversible adiabatic pumping process in the feed pump, and 4 to 1 shows the constant pressure transfer of heat in the boiler. Here we will see the working of Rankine cycle one by one. It is, hence we have already discussed, the Rankine cycle is a theoretical framework that describes the process by which heat is converted into mechanical work in a steam turbine. The component, a boiler or heat source, a steam turbine, a condenser and a pump. Boiler, or generally it is called as heat source. The cycle begins in the boiler, where a heat source, often fossil fuel like coal, natural gas or nuclear reactions, is used to generate high temperature and high pressure steam. The heat source raises the temperature and pressure of water, causing it to boil and turn into superheated steam. Then we will discuss about the steam turbine. The high pressure, high temperature steam is directed into steam turbine. As the steam flows through the turbine blades, it expands and does its pressure and temperature lower. The expansion of the steam causes the turbine blades to rotate, which is connected to a generator that produces electricity. Now about the condenser. After passing through the turbine, the low pressure, low temperature steam exists and enters a condenser. In the condenser, the steam is condensed back into liquid water. Heat is transferred from the steam to a cooling medium, usually water from a cooling tower or river, to facilitate the condensation process. Coming to the pump, the fourth component of Rankine cycle, the condensate water, now at a low pressure, is pumped back to the boiler to restart the cycle. The pump consumes some energy to increase the pressure of the water, which condensates for the energy extracted by the turbine. The Rankine cycle is a continuous loop where water is continuously heated, expanded in the turbine to produce mechanical work, condensed back into a liquid and then pumped back to the boiler to repeat the cycle. The work produced by turbine is used to generate electricity, and the cycle's efficiency depend on various factors including the temperature and pressure level in the boiler and condenser. This process starts with a feed pump. The feed pump supplies the water in necessary amount to the steam boiler. In this device, heat is supplied from supplied water. When the steam is generated, it is transferred to the steam turbine and turbine starts to rotate and get the work done. After this, the steam is transferred to the steam condenser, where the heat is rejected and steam is converted into hot water, and it is converted into cool water, which is supplied to the pump, and the cycle repeats again and again, and ultimately we are able to get the work done. Here we can see the TS diagram of Rankine cycle 1 to 2 and 2 to 3 and 3 to 4 and 4 to 1. So, here in this picture we are able to see that we are giving some amount of work in case of 1 to 2, that is pump work, and in 2 to 3 we are able to see here in this picture that work is done, we are getting work done from the turbine. So, here in this case we can say the net work we can get after the completion of one cycle of the Rankine cycle. As here we can discuss the summary of Rankine cycle. Process 1 to 2, that is the isotropic compression. The working fluid is pumped from low to high pressure. As the fluid is a liquid at this stage, the pump requires little input energy. The high pressure liquid enters a boiler, where it is heated at constant pressure by an external heat source to become a dry saturated vapor. The input energy required can be easily calculated graphically using an enthalpy entropy chart, that is called as HS diagram or Molière diagram, or numerically using steam tables or software. Now, here we can see the process 2 to 3 is a constant pressure heat addition in boiler, and the process 3 to 4 shows isentropic expansion. The dry saturated vapor expands through a turbine generating power. This decreases the temperature and pressure of the vapor, and some condensate may occur. The output in this process can be easily calculated using the chart or tables. Process 4 to 1 shows the constant pressure heat rejection in condenser. The wet vapor then enters a condenser, where it is condensed at a constant pressure to become a saturated liquid. Here in this picture we can see the diagram for Rankine cycle. PV and TS diagram is shown here in this slide. So, as we have discussed in previous slide, process 1 to 2 shows the isentropic compression, process 2 to 3 shows the constant pressure heat addition, and process 3 to 4 shows isentropic expansion, and process 4 to 1 shows constant pressure heat rejection in condenser. Now, here we can see the energy analysis in case of Rankine cycle. Rankine cycle consists of the following processes. 1 to 2 is reversible adiabatic process in the turbine. The process is becoming in the turbine, and 2 to 3 is the constant pressure transfer of heat in the condenser, and 3 to 4 is reversible adiabatic pump process in the feed pump, and 4 to 1 shows the constant pressure transfer of heat in the boiler. Rankine cycle on PV and TS diagram are shown in this slide. So, if I am going to consider 1 kg of fluid applying steady flow energy equation SFEE to boiler, turbine, condenser and pump, then we can get the equation here. Boiler HF4 plus Q1 is equal to H1, Q1 is equal to H1 plus HF4. In case of turbine as control volume, here we can get the value of H1, that is enthalpy at point 1, is equal to WT turbine work plus H2, and WT can be calculated as equal to H1 minus H2, where WT is work done by the turbine. In case of condenser, we can calculate the value of H2, that will be equal to Q2 plus HF3, and Q2 is equal to H2 minus HF3. In case of feed pump, HF3 plus WP. WP is the pump work, will be equal to HF4, and WP can also be calculated as HF4 minus HF3. So, this is the energy equation, energy analysis in case of Rankine cycle. We will talk about the efficiency of Rankine cycle. The efficiency of ideal Rankine cycle is defined as the ratio of net work done by the steam turbine power plant, that is denoted as W net, and heat supplied to the boiler QS. The differences between turbine work WT and pump work input, that is WP, is defined as the net work done, that is W net. Here in this slide we are able to see the case of efficiency of Rankine cycle. So, how the efficiency of Rankine cycle can be calculated? The equation shows the method of calculation of the efficiency of the Rankine cycle. Thermal efficiency improvement. Now, question arises, can we improve the efficiency of Rankine cycle? The answer is yes, we can improve the efficiency of the Rankine cycle. Now, we can discuss one by one the method of improvement of Rankine cycle using various systems. So, here we can say that we can improve the efficiency of Rankine cycle by regenerative feed heating, by reheating of steam, by water extraction, by using binary vapor. Here we can say some cases are there. Using these accessories we can improve the efficiency of Rankine cycle. Like number one is superheating. Superheating the steam before it enters the turbine can increase efficiency. Superheated steam consists more energy and can do more work in turbine compared to saturated steam. Second one is reheat. In a reheat Rankine cycle, the steam is expanded through the turbine and then partially condensed before being heated again and expanded through a second turbine. This process increases the average temperature of heat addition, improving efficiency. Next method is regeneration. Regeneration involves extracting heat from steam at its exit the turbine and using it to preheat the feed water before it enters the boiler. This reduces the amount of heat needed to be added in the boiler, improving overall efficiency. Cooled condensers, lowering the temperature of the condenser or using a cooling medium that has a lower temperature than the ambient air, such as water vapor, water from a river, or a cooling lower, can increase the temperature difference in the calculated form. Next method is high pressure and low pressure turbine. Using multiple stages of turbine with different pressure levels can increase efficiency of the Rankine cycle. High pressure turbine handle the initial expansion, while low pressure turbine handle the remaining expansion. Next method is combined heat and power system. Utilize the waste heat generated in Rankine cycle for heating process such as district heating or industrial processes to increase overall system efficiency. Next method we can apply is advanced material. Using advanced materials in the construction of boiler, turbine and condensers can reduce energy losses due to heat transfer and friction, ultimately increasing the efficiency. Next we can use is improved insulation. Properly insulating components like boiler, pipes and valves can reduce heat losses, which can significantly impact overall efficiency. Next method is variable geometry turbines. Implementing variable geometry turbines allows for better matching of turbines performance to varying load conditions, maximizing efficiency across a range of operating conditions. Next method we can apply is advanced control system. Implementing advanced control system and predictive maintenance technique can optimize the operation of the Rankine cycle and identify opportunities for efficiency improvement. Next, we can go for hybrid cycle, combining the Rankine cycle with other cycles such as Brayton cycle using in gas turbines. In a combined or hybrid cycle can increase overall efficiency of the Rankine cycle. Now, next we can use is optimized working fluid. Research into advanced working fluids such as supercritical carbon dioxide or other innovative substances can lead to higher efficiency by improving the thermodynamic properties of the cycle. Next is advanced cycle. Explore more advanced dynamic cycle like organic Rankine cycle, this is called as ORC, or the Kalina cycle, which are designed for specific applications and may offer higher efficiencies in certain conditions. The specific techniques chosen for improving Rankine cycle efficiency will depend on the applications, available technologies, and economic considerations. Engineers and researchers continue to explore new methods and technologies to enhance the performance of Rankine cycle based power generation system. Here in this case, we can see the comparison between Carnot cycle and Rankine cycle. Of course, Carnot cycle is called as an ideal cycle and Rankine cycle is called as a practical cycle. In this slide, we can see the TS diagram of Carnot cycle and Rankine cycle in a single slide. Comparing the Carnot cycle and Rankine cycle, as the number one point in Carnot cycle is a theoretical cycle. It gives maximum efficiency between two temperature differences, whereas the Rankine cycle is a practical cycle of a steam engine and turbine. In case of Carnot cycle, heat is added and rejected at constant temperature, whereas in case of Rankine cycle, heat is added and rejected at constant pressure. In case of Carnot cycle, it has a highest efficiency between two temperature differences, whereas Rankine cycle has lower efficiency than Carnot cycle. Carnot cycle uses air as the working substance and Rankine cycle uses water as working substance. Carnot cycle is an ideal cycle for heat engine, whereas the Rankine cycle is an ideal cycle for vapor power engine. Now, we can give an overview of Rankine cycle because we are focusing in this session on Rankine cycle. The Rankine cycle is the thermodynamic cycle used in steam power plants, including fossil fuel, nuclear, and some renewable energy power plants to convert heat into mechanical energy. The Rankine cycle consists of four main processes: compression, heating, expansion, and cooling. Let us see one by one what happens in compression and heating and expansion and cooling. In case of compression, the cycle begins with a pump that compresses a lower pressure, high volume liquid, usually water, to a high pressure, high energy state. The compression process is typically assumed to be isentropic, meaning there is no heat exchange with the surroundings and the entropy remains constant. The second case is heating, isobaric heat addition. The high pressure liquid is then sent to a boiler or heat exchanger where it is heated at constant pressure. In the boiler, liquid is exposed to a heat source, usually combustion of fossil fuels or nuclear reactions, to convert it into high temperature, high pressure vapor steam. During this process, the enthalpy of the fluid increases, it absorbs heat energy. Third portion is expansion, isentropic expansion. The high pressure steam of the boiler is directed to a turbine where it undergoes an isentropic expansion. As the steam expands through the turbine blade, it does work by running the turbine rotor, which drives a generator to produce electricity. The expansion process causes a decrease in pressure and temperature. The steam loses energy. The fourth process is isobaric heat rejection, that is called as cooling. After passing through the turbine, the low pressure, low temperature steam is condensed back into a liquid by passing it through a condenser. The condenser transfers heat from the steam to a cooling medium, usually water from a cooling tower or a river, causing the steam to condense. Efficiency improvement in Rankine cycle can be achieved through techniques like reheating, regeneration and supercritical operation, all of which are designed to maximize utilize the heat input and minimize heat losses, making power generation more efficient and cost effective. Steam power plants are responsible for the production of most electric power in the world. Even a small increase in thermal efficiency can mean large saving from the fuel requirements. The basic idea behind all modifications to increase the thermal efficiency of power cycle is the same. The average temperature should be as high as possible during the heat addition and as low as possible during the heat rejection. So, this is the overview of Rankine cycle. Thank you. Namaskar.